So that's the gist of the IBD monitor, and we had a number of early adopters in last fall, and we learned a ton. I just wanted to share 3 examples of these of some drying events, just so you can get a bit of a feel for the type of data and what you can learn from this data. The first drying event is 4,500 bushels of yellow peas. We had a 5-horse turbo inline centrifugal fan, so it's a slightly premium fan, just has a little more airflow for that 5 horsepower. We were moving 5,000 CFM, which is about 1.1 CFM per bushel. Poor drying conditions, daytime highs of 20 maybe, and 60% humidity, and we had nighttime lows of 10 degrees and pretty much 100% humidity. We're going with no supplemental heat and an 8-foot by 24-inch aeration duct, so just a standard aeration duct. And I guess we're going with no supplemental heat, as many farmers do with their peas, because I guess the thought is that in most instances, peas are very easy to aerate and very easy to dry down. Here's our first plot. This is a temperature plot with also with the water removal rates. The lighter pink color is our ambient temperatures, and the dark red color is the plenum temperature. You can see we have no supplemental heat, but even with that, the plenum temperature is slightly warmer, and the reason for that is when the fan does impart some energy into the airstream, so there is some heat of the slight compression that's happening, but also this is an inline centrifugal fan, so we're capturing all the heat from that motor, so that will also contribute to that bump. Now, looking at the blue curve here, you can see that initially we got some really good water removal. We were over 15 gallons per hour the first 3 hours, and that also was extremely common because you have the warm grain in the bin, and cooling that grain is what really kicks out the big amounts of moisture. But then, as soon as we got further on here, I'm just adding the 0 line. You can see that we actually were below 0 for a number of hours, and coincidentally, those hours are associated with the heat of the day. So here we had one day that we were over 20 degrees, and we were adding water during the day, and the next day we were at about 17 degrees ambient, and we were again adding water. And if you look here, this is during the night. We were during the night we were actually taking water out. So this really corresponds exactly to Ron Palmer's research at Indian Head back in 2013, and it sort of introduced the whole concept of only run your fans at night. Now, obviously, based on our instrumentation, we're confirming his research. It's saying the exact same thing. But the one problem with that logic is that in an instant like this, where you have 1 point tough, you can maybe, by cooling it, maybe you'll have enough BTUs in that grain mass to get your grain dried. But if you have 4 points or 5 points of drying to do, there's no chance that you're going to have enough BTUs in your grain mass to evaporate all your water. So to just cool the grain and just run your fans at night is going to result in a really cold bin of very tough grain. The only way that you can actually dry grain is by adding the BTUs and adding and evaporating that water. So yeah, if you have 1 point to dry, potentially cooling alone will get you there. But this just sort of is a nice illustration of what is required. Here is a plot of the bin average moisture content. You can see we started out only at 16.8 or 16.9, and through the first 20 hours, we dried it down to about 16.5, and the next 100 hours, we wasted our time and money. This is just a plot of the ambient humidity and how it impacts or how it impacts our water removal rates. You can see here early on, we actually had very low humidity, and that helps out with our water removal rates. During this time frame, we were at 100% humidity, so the fan was actually turned off. And then here we ran it through the rest, but again, you can see we had pretty poor drying conditions with 80% or above humidity for the majority of that drying event. Here's a plot of our costs. This here light green line is the cumulative cost through the drying event. You can see here, this is basically just a fan running. So there's a pretty shallow curve. Here the fan was shut off. Our total cost for that was about just under $60, about $57 it cost us to dry it that half a point. And that works out to 3.2 cents per bushel, which isn't bad, but it could have been quite a bit better if we hadn't wasted time. I mean, if you look here, after 20 hours, we only had burnt about $12 worth of costs, so we could have saved the majority, and we would have had some really efficient drying costs.